Hello there, and welcome back to the Sleep Science. Tonight you find yourself standing beneath a sky so clear it feels almost artificial, like someone polished the universe just for you. The stars don't just twinkle, they press in, countless and sharp, stretching in every direction. You tilt your head back and feel that familiar mixture of awe and mild existential vertigo, because up there is everything. And according to our best models, we understand it pretty well. Or at least, we think we do. You're standing on a small planet orbiting an average star in a typical spiral galaxy. The universe began 13.8 billion years ago in a hot, dense state called the Big Bang. It expanded, cooled, formed atoms, stars, galaxies. Most of its mass is dark matter. Most of its energy is dark energy. Space-time curves, gravity-shaped structure. It's neat, it's elegant. It fits the data impressively well. But here's the quiet, slightly unsettling thought. What if the universe isn't what we think it is? You probably won't survive a complete collapse of cosmological certainty, by the way. Humans get twitchy when their cosmic maps are redrawn. Just ask anyone who lived through the Copernican revolution. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, tell me where you're listening from and what your local time is. It's oddly grounding to know what tiny patch of Earth you occupy while we question the entire cosmos. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You gaze upward again. Our current cosmic blueprint is called the Lambda-CDM model. Lambda represents dark energy, the mysterious force driving the accelerated expansion of the universe. CDM stands for cold dark matter, the invisible substance that provides gravitational scaffolding for galaxies. This model explains an extraordinary range of observations: the cosmic microwave background radiation, galaxy clustering, gravitational lensing, the large-scale web of cosmic structure. That's a mainstream fact. The model works stunningly well in many respects. But here's the subtle tension. About 95% of the universe, according to this model, is made of things we cannot directly detect. Dark matter has never been observed in a laboratory. Dark energy has never been isolated, bottled, or meaningfully characterized beyond its large-scale effects. You're left with a peculiar situation. The most successful cosmological model in history depends primarily on invisible components. It's a bit like confidently describing a cake recipe when you can only see the frosting. Historians still argue whether this represents a triumph of inference, deducing the unseen from gravitational fingerprints, or whether it hints that our underlying assumptions about gravity and space-time might be incomplete. You imagine being a physicist in the early 20th century. Newton's laws had reigned for centuries. Then small anomalies like the orbit of Mercury refused to fit perfectly. Enter Einstein, who reframed gravity not as a force but as curvature of space-time. The old model wasn't useless. It was incomplete. Could something similar be happening now? You consider the Big Bang itself? The evidence for a hot, dense early universe is overwhelming. The cosmic microwave background radiation discovered in 1965, the abundance of light elements like helium and deuterium, the observed expansion of space. These are not speculative, they are measured facts. But what happened before the Big Bang, or at the very first fraction of a second? Our equations break down at a singularity, an infinite density point where general relativity stops behaving sensibly. That's not satisfying, that's a placeholder. A quirky but telling detail: the term Big Bang was originally coined mockingly by astronomer Fred Hoyle, who favored a steady-state universe. The name stuck anyway. Science has a sense of humor like that. You let that irony settle in, even our terminology began as skepticism. And so tonight, you're not discarding everything we know. You're gently loosening your grip on certainty. Because history shows that whenever humans believe they have reached the final cosmic picture, the universe politely rearranges it. Earth was once the center. Then the sun was. Then our galaxy. Then we discovered billions more galaxies. Each time, the shift felt destabilizing and then became normal. Historians still argue whether we are nearing a theory of everything that will unify gravity and quantum mechanics, or whether reality may be fundamentally resistant to total explanation. You stand beneath the sky, feeling both small and strangely empowered. Small because the universe is vast beyond comprehension. Empowered because you're a part of a species that dares to question its own cosmic assumptions. What if dark matter isn't a particle, but a misunderstanding of gravity? What if dark energy isn't energy at all, but a sign that space-time behaves differently on enormous scales? What if the universe is only one region in a far larger structure? None of these questions are wild fantasies. They're active areas of research, debated in journals and conferences, Looking up at the stars, you realize something soothing. The universe does not need to be exactly what we think it is for it to be beautiful. But if it isn't what we think, it may be even stranger. And tonight, you begin with the simplest act of rebellion in science. You allow the possibility that the blueprint is provisional, that what feels like a finished map might still be a draft. The stars shine calmly overhead, indifferent to your curiosity. But your curiosity remains, and that's where every cosmic revision begins. You stay beneath that vast sky, but now you let your mind rewind, back past galaxies, past stars, past atoms, to the beginning. Or at least what we call the beginning, the Big Bang. It's often described as an explosion, but that's misleading. It wasn't matter blasting outward into empty space. It was space itself expanding. Every point moving away from every other point. No center, no edge, just expansion everywhere at once. A mainstream fact anchors this firmly. In 1929, Edwin Hubble observed that distant galaxies are receding from us and that their recession speed increases with distance. This relationship, Hubble's law, provided the first strong evidence that the universe is expanding. Later in 1965, the discovery of the cosmic microwave background radiation sealed the case for a hot, dense early universe. The cosmic microwave background, CMB for short, is faint radiation that fills all of space, a leftover glow from when the universe was about 380,000 years old. Its temperature is an almost perfectly uniform, 2.7 degrees above absolute zero. Tiny fluctuations in that temperature map the seeds of future galaxies. That's not speculative. We've measured it with satellites like COBE, WMAP, and Planck. The data is astonishingly precise. So when someone asks, is the Big Bang real? The honest answer is, the evidence for a hot, dense early phase is overwhelming. But here's where it gets interesting. The equations of general relativity, when run backward in time, lead to a singularity, an infinitely dense point where the math breaks down. Physicists don't like infinities in their equations. They usually signal that the theory is being pushed beyond its limits. Historians still argue whether the singularity represents a real physical beginning of space and time, or simply a boundary where general relativity must give way to a quantum theory of gravity. Because here's the problem. General relativity describes gravity beautifully on large scales. Stars, galaxies, cosmic expansion. Quantum mechanics describes the microscopic world, particles, fields, uncertainty. But the two frameworks don't merge cleanly. At extreme densities, like those near the supposed beginning, both should apply, and they clash. You imagine zooming backward in time. The universe shrinks, galaxies compress into a hot plasma. Protons and electrons dissolve into quarks and gluons. Eventually, densities become so extreme that space-time itself might fluctuate quantum mechanically, and then our equations stop cooperating. A quirky but fascinating detail: some alternative cosmological models propose that the Big Bang was not the absolute beginning, but a bounce. In these scenarios, a previous universe collapsed under gravity and then rebounded into expansion. Instead of a singular start, there's a cyclic rhythm: collapse, bounce, expansion. It sounds almost poetic, cosmic breathing. But is there evidence? Not yet decisive. Some models predict subtle imprints in the cosmic microwave background, specific patterns in polarization or temperature fluctuations. So far, observations are consistent with inflationary Big Bang cosmology, but not precise enough to rule out all bounce scenarios. Ah yes, cosmic inflation. That's another layer. According to mainstream theory, a fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion, growing exponentially in size in less than a trillionth of a second. Inflation explains why the universe appears so flat and uniform on large scales. The evidence for inflation is indirect but compelling. The flatness of spacetime, the specific statistical distribution of CMB fluctuations. Historians still argue whether inflation is a single elegant mechanism or a broad class of models so flexible they risk explaining almost anything. Some physicists worry it's too adaptable. Others see it as the best explanation we have. You feel the subtle shift again. The Big Bang model is strong, but the earliest instance before 10,030 seconds are speculative territory. What if inflation never happened? What if space-time behaves differently at extreme scales? What if the Big Bang was not the beginning, but a transition? These questions are not science fiction. They are serious research topics. You imagine standing at the edge of a waterfall, watching water plunge into mist. You can see everything clearly until it hits the turbulence below. That mist is like the Planck epoch, the earliest moment, around 10 to the power of 3 seconds after the Big Bang, our physics dissolves there. Beyond that, we don't know. And here's the gentle, unsettling thought. If our understanding of the beginning is incomplete, then everything built upon it, cosmic timelines, expansion histories, structure formation, rests on assumptions that may someday be refined, not discarded entirely, but reshaped. A mainstream anchor keeps you steady. Big Bang nucleosynthesis, the formation of light elements in the first few minutes, matches observed abundances of helium and deuterium with remarkable precision. That's powerful confirmation. Yet even within that success lies humility. We know what happened minutes after the beginning. We do not know what happened at the beginning. Historians still argue whether science will ever fully penetrate that earliest boundary, or whether there will always be a horizon beyond which explanation dissolves into speculation. You look up again at the stars, the universe feels stable, ancient, expansive. But its origin story still contains fog. And if the beginning is not exactly what we think it is, if there was a bounce or a prior phase or a deeper layer of physics, then the entire cosmic narrative might stretch further than we've imagined. The Big Bang may be the opening chapter, or it may be the middle of a much longer book. Now you let your mind drift from the beginning of time to something equally mysterious, something that surrounds you right now, threads through galaxies, shapes cosmic structure, and yet has never been seen: dark matter. You're standing again beneath that clear night sky. The Milky Way stretches overhead like spilled sugar. It looks serene, balanced, graceful. But if you could measure the speeds of stars orbiting the galactic center, you'd notice something strange. A mainstream historical fact grounds this. In the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies and found that stars far from the center were orbiting much faster than expected. According to Newtonian gravity, orbital speed should decrease with distance from the center, much like planets in our solar system. Instead, the rotation curves were flat. The outer stars were moving too fast. If only visible matter were present, galaxies should fly apart. So scientists proposed an invisible mass, dark matter, surrounding galaxies in vast halos, providing the extra gravitational pull needed to hold them together. That idea explains not just galaxy rotation curves, but also gravitational lensing, the bending of light around massive clusters, and the way galaxies cluster across enormous cosmic scales. Simulations using cold dark matter reproduce the large-scale cosmic web remarkably well. By most estimates, dark matter makes up about 85% of the universe's total matter content. Pause there. 85% of matter is invisible. You don't see it. You don't feel it. It doesn't interact with light. It doesn't clump into stars or planets. It passes through you constantly without a whisper. And we have never directly detected a dark matter particle in a laboratory. That's not for lack of trying. Underground detectors shielded from cosmic rays search for faint particle interactions. Particle accelerators attempt to create candidate particles. So far, nothing definitive. Historians still argue whether dark matter is a new kind of particle, perhaps a WIMP, weakly interacting massive particle, or an axion, or whether the phenomenon reflects a misunderstanding of gravity itself. Because here's the alternative. What if gravity behaves differently on galactic scales? There's a framework called MOND, Modified Newtonian Dynamics, that proposes gravity strengthens slightly at very low accelerations, eliminating the need for dark matter in explaining galaxy rotation curves. MOND can successfully predict certain galactic behaviors with surprising accuracy, but MOND struggles to explain large-scale structure and observations of the cosmic microwave background as effectively as dark matter models do. So you're left in a curious position. Dark matter fits the data beautifully on cosmic scales, but remains undetected directly. Modified gravity explains some galactic behaviors elegantly, but faces challenges elsewhere. A quirky but telling detail: in 2006, astronomers observed the Bullet Cluster, two colliding galaxy clusters, and found that the majority of gravitational mass was offset from the visible hot gas. This observation strongly supported the existence of dark matter, because the gravitational lensing map did not align with ordinary matter alone. Many physicists consider this one of the strongest pieces of evidence for dark matter's reality, and yet the particles remain elusive. You imagine standing in a dark room, feeling objects around you without seeing them. You can map their presence by how they push and pull, but never catch a glimpse. That's dark matter. Historians still argue whether we are on the brink of detecting it directly, or whether decades from now we may look back and realize we misinterpreted gravitational phenomena entirely. Because here's the deeper possibility. What if dark matter is neither a particle nor modified gravity, but something even stranger? A manifestation of extra dimensions? A sign that space-time has additional structure at large scales? Some theories propose that gravity leaks into higher dimensions, weakening its apparent strength in ways that mimic dark matter effects. These ideas are speculative, yes, but not whimsical. They arise from attempts to reconcile gravity with quantum theory. You feel the weight of it again. If dark matter is real, then most of the universe's matter is fundamentally different from anything you've ever touched. If dark matter is not real, if it's a placeholder for deeper gravitational physics, then our understanding of space-time may be incomplete. Either way, the universe is not quite what it seems. A mainstream anchor keeps you steady. The Lambda-CDM model, including dark matter, matches observations of large-scale structure and the cosmic microwave background with remarkable precision. That success cannot be casually dismissed, but absence of direct detection leaves a sliver of doubt. And doubt in science is not weakness. It's motivation. You look up at the Milky Way again. The stars orbit calmly, unaware of the invisible halo shaping their motion. You imagine dark matter particles streaming silently through Earth, through your body, through everything, trillions per second, ghostly and indifferent. Or perhaps, just perhaps, gravity itself is whispering that we haven't fully understood it yet. Historians still argue whether the discovery of dark matter will mirror the discovery of Neptune, predicted from gravitational anomalies before being observed, or whether it will resemble the abandonment of the luminiferous ether, once proposed to explain light propagation before relativity rendered it unnecessary. That's the fork in the road. Is dark matter Neptune, or is it the ether? You stand beneath the stars, breathing slowly. If the universe isn't what we think it is, dark matter is one of the first cracks in the facade. Either it reveals a hidden particle world vastly outweighing everything familiar, or it reveals that gravity itself is deeper and stranger than we've imagined. And in either case, the night sky above you is not as simple as it looks. Now you shift from the invisible mass holding galaxies together to something even stranger, something that isn't pulling inward, but pushing outward. Dark energy. You're still under that same night sky, but this time imagine zooming out, far beyond the Milky Way, beyond local galaxy clusters, into the vast cosmic web. Galaxies aren't just drifting apart. They're accelerating away from one another. That discovery came as a shock. A mainstream historical fact anchors this moment. In 1998, two independent teams studying distant type Ia supernovae discovered that the universe's expansion is accelerating. These supernovae act as standard candles because their intrinsic brightness is well understood. By comparing their known brightness to how bright they appear, astronomers can measure cosmic distances. What they found was unsettling. Distant supernovae were dimmer than expected, not because they were farther in a slowing universe, but because the expansion of space had sped up over time. Gravity, which should slow expansion, wasn't winning. Something else was dominating on large scales. That something was labeled dark energy. Today, according to the standard cosmological model, dark energy makes up about 68% of the total energy content of the universe. More than dark matter, more than ordinary matter. You let that sink in. Most of the universe isn't matter at all. It's a kind of energy associated with empty space itself. The simplest explanation is Einstein's cosmological constant, represented by the Greek letter lambda. Interestingly, Einstein originally introduced this constant into his equations to allow for a static universe, then later called it his biggest blunder after the discovery of cosmic expansion. Now, it's back. If dark energy is a cosmological constant, then empty space has an intrinsic energy density. As space expands, more space exists, so more dark energy exists. The effect doesn't dilute like matter does. It remains constant per unit volume, causing acceleration to dominate over time. It's elegant, it fits the data well. But here's the tension. Quantum field theory predicts that empty space should have vacuum energy due to fluctuations in quantum fields. When physicists calculate that vacuum energy, they get a value vastly larger, by a factor of up to 10 to the 12.3, than what is observed cosmologically. That's not a small discrepancy. That's the worst theoretical prediction in physics. Historians still argue whether this enormous mismatch signals a profound misunderstanding of vacuum energy, or whether some unknown cancellation mechanism reduces the effective cosmological constant to its tiny observed value. You imagine trying to balance a scale with weights that differ by 120 orders of magnitude and somehow landing on perfect equilibrium. It feels improbable. So some physicists explore alternatives. What if dark energy isn't constant? What if it evolves over time? There are models called quintessence, where dark energy arises from a dynamic field that changes as the universe expands. Others propose modifications to general relativity on cosmic scales, altering how gravity behaves at extreme distances. Because here's the possibility. Maybe cosmic acceleration isn't due to mysterious energy at all. Maybe our equations for gravity are incomplete at vast scales. Just as Newton's laws required refinement by Einstein, perhaps Einstein's equations require refinement by something deeper. A quirky but fascinating idea. Some theories suggest that the acceleration could be a side effect of extra dimensions or large-scale geometric effects in spacetime. In these scenarios, the universe's expansion isn't being pushed by energy, it's unfolding in a higher dimensional structure we barely perceive. It sounds exotic, but so did curved spacetime once. A mainstream anchor keeps you grounded. Multiple independent observations confirm cosmic acceleration, supernovae, cosmic microwave background measurements, and large-scale galaxy surveys all converge on the same conclusion. The acceleration is real. What's uncertain is its cause. Historians still argue whether dark energy represents a fundamental constant of nature or a placeholder term masking deeper physics yet to be uncovered. You let your mind drift far into the future. If dark energy continues to dominate, galaxies beyond our local group will eventually recede beyond our observable horizon. In trillions of years, distant galaxies will disappear from view entirely. Future astronomers, if any exist, might see only their own gravitationally bound cluster and conclude they live in a static, lonely universe. That's not speculation. It's a prediction of current models. So dark energy doesn't just shape cosmology, it shapes the ultimate fate of everything. Heat death, endless expansion, increasing isolation, unless, of course, dark energy changes. Some speculative models predict a big rip where acceleration intensifies until galaxies, stars, planets, even atoms are torn apart. There's no evidence this is happening, but the equations allow for such possibilities under certain parameters. You breathe slowly. If dark energy is real and constant, then most of reality is driven by a quiet property of empty space. If dark energy is something else, an evolving field, modified gravity, higher dimensional geometry, then spacetime itself may be more dynamic than we realize. Either way, the emptiness between galaxies is not empty. It's active. You look up at the stars again, imagining the space between them stretching ever so slightly faster with each passing moment. Historians still argue whether dark energy will be understood as a simple constant or as the doorway to a new era of gravitational physics. For now, it remains the most dominant and least understood component of the cosmos. If the universe isn't what we think it is, dark energy may be the biggest clue. Because when empty space itself drives cosmic destiny, you have to admit, reality might be stranger than the blueprint suggests. Now you let go of galaxies and expansion entirely and turn to something even more intimate, something you've been standing inside this whole time. Space-time itself. You've been treating space as a stage and time as a ticking clock. Events happen somewhere, sometime, clean, linear, comfortable. But what if space and time aren't fundamental? You look up at the stars again, but this time imagine that the fabric of space-time is not a smooth continuum. In Einstein's general relativity, space-time is a geometric structure that curves in response to mass and energy. That curvature tells matter how to move. It's elegant. It works astonishingly well. Gravitational waves, ripples in space-time, were directly detected in 2015 by LIGO, confirming Einstein's prediction from 1916. That's a mainstream triumph of physics. Space-time behaves exactly as the equations describe, at least on large scales. But zoom in far enough down to the Planck length, around 10 meters of the Earth 50 meters, and the smooth geometry may dissolve into something granular, quantum, jittery. At that scale, general relativity and quantum mechanics refuse to cooperate. One describes smooth curvature. The other describes probabilistic fields fluctuating with uncertainty. Historians still argue whether space-time is a fundamental entity or an emergent phenomenon, something that arises from deeper, more primitive ingredients. Think about temperature. You experience it as a smooth quantity, but temperature isn't fundamental. It emerges from the motion of countless microscopic particles. On its own, a single atom doesn't have temperature. Temperature arises statistically. What if space-time is like that? What if space and time emerge from something more basic? Quantum bits of information, entanglement networks, microscopic building blocks that don't resemble geometry at all? There's a growing line of research suggesting exactly that. In certain approaches to quantum gravity, like loop quantum gravity, space may be composed of tiny discrete units, almost like pixels of geometry. In string theory, the fundamental objects aren't points but tiny vibrating strings existing in higher dimensional space. A quirky but fascinating idea comes from the study of quantum entanglement. Some physicists propose that space-time geometry itself may arise from patterns of entanglement between quantum systems. In this view, the connectivity of space is built from informational relationships. It's as if space is stitched together by quantum correlations. And here's the strange implication. If entanglement structures define geometry, then distance itself may be secondary. Two regions of space could be close not because of physical proximity, but because of strong quantum connections. You pause. Distance might be relational. That's a radical shift from everyday intuition. A mainstream anchor steadies you. While these ideas are mathematically intriguing, no complete, experimentally verified theory of quantum gravity yet exists. We know space-time behaves classically at large scales and quantum mechanics governs particles at small scales, but merging them remains one of the greatest open problems in physics. Historians still argue whether the solution will resemble existing frameworks like string theory or loop quantum gravity, or whether it will require an entirely new conceptual leap. You imagine space-time not as a smooth ocean, but as a shimmering foam at microscopic scales, a concept sometimes called quantum foam, originally suggested by John Wheeler. At incredibly small distances and times, space-time may fluctuate violently, bubbling with transient geometries. If that's true, then the universe is not a rigid arena. It's dynamic at its deepest level. And here's where it becomes truly unsettling. If space-time is emergent, then what we perceive as reality, locations, durations, separation, may be like surface-level phenomena. Underneath, the universe could be structured more like a computational network or an informational web. Historians still argue whether information, rather than matter or energy, might be the most fundamental currency of the universe. The idea gained traction with black hole thermodynamics, where physicists discovered that black holes have entropy proportional to their surface area, suggesting deep connections between gravity, information, and geometry. You imagine standing at the edge of a black hole's event horizon. According to mainstream physics, information about matter falling into the black hole is not destroyed. It is encoded somehow on the horizon surface. That insight led to revolutionary thinking about the nature of space itself. If geometry can encode information, maybe geometry isn't primary, maybe information is. You breathe slowly beneath the night sky. If space and time are emergent, then the universe isn't a static stage where events unfold. It's a dynamic structure arising from deeper principles we're only beginning to glimpse. That would mean that asking, "Where did the universe begin?" might be like asking, "Where does temperature begin?" The question assumes a fundamental status for something that might itself be derivative. Historians still argue whether such ideas are speculative philosophy or the frontier of serious physics. But increasingly, they are appearing in peer-reviewed research, not just late-night dorm room debates. You look around you, trees, air, stars, distances measured in meters and light years, time ticking forward. All of it might be the macroscopic expression of something far stranger. If the universe isn't what we think it is, perhaps the most radical possibility is this. Space and time themselves are not the foundation. They are the surface. And beneath that surface lies a deeper architecture. Still hidden, still mathematical, still waiting to be understood. Now that you've loosened space-time itself, you're ready for something even more disorienting. What if the universe is, in some profound sense, a hologram? You stand beneath the night sky again, but imagine that everything you see, the stars, galaxies, even your own body is not the full story. Instead, it's a projection. Not fake, not illusory in the everyday sense, but encoded on a distant boundary in a way that makes 3 dimensions emerge from 2. This idea is called the holographic principle. A mainstream historical anchor grounds it. In the 1970s, physicists studying black holes, most notably Jacob Bekenstein and Stephen Hawking, discovered that black holes have entropy proportional not to their volume, but to the area of their event horizon. That was shocking. In normal thermodynamics, entropy scales with volume, but black holes seem to encode their information on a surface. Later in the 1990s, physicists Gerard 't Hooft and Leonard Susskind proposed that this might be a universal feature. Perhaps all the information contained within a region of space can be described by information encoded on its boundary, like a hologram. A hologram is a 2-dimensional surface that encodes a 3-dimensional image. When illuminated properly, depth appears. The holographic principle suggests that our 3D universe could be the projection of information stored on a distant 2D boundary, perhaps at the edge of the observable universe. You pause. This is not science fiction. It arises from attempts to reconcile quantum mechanics and gravity. In 1997, Juan Maldacena proposed a concrete mathematical realization of this idea called the ADS-CFT correspondence. In simplified terms, it demonstrated that a gravitational theory in a higher dimensional bulk space could be equivalent to a quantum field theory on its lower dimensional boundary. Two very different descriptions, one with gravity, one without, produce the same physics. That's a mainstream theoretical milestone. It doesn't prove our universe is holographic, but it proves such dualities are mathematically consistent. Historians still argue whether this duality is a special case applying only to certain idealized spacetimes, or whether it hints at a deep, universal truth about reality. You imagine the observable universe as the inside of a cosmic sphere. Every event, every star, every particle interaction encoded somehow on its boundary. The depth you perceive, distance between galaxies, the curvature of spacetime, emerges from information relationships on that surface. It feels abstract, but then again, so does curved spacetime until you see gravitational lensing bend light around a cluster of galaxies. A quirky but fascinating detail, some physicists have found that certain calculations of black hole entropy and quantum entanglement only make sense if information is fundamentally two-dimensional in specific contexts. The math keeps pointing back to surfaces encoding volumes. And here's the gentle twist. If the universe is holographic, it doesn't mean your life is fake. It means the way information is organized at the deepest level might not match your everyday intuition about dimensions. 3 dimensions could be emergent. Depth could be derived. Historians still argue whether experimental evidence could ever confirm holography directly. Some researchers look for subtle imprints in cosmic microwave background fluctuations or quantum noise patterns that might hint at underlying discrete informational structure. So far, no definitive signature has been found. But the idea persists because it elegantly connects gravity, thermodynamics, and quantum information. You imagine standing at the edge of a black hole again. The event horizon glows faintly with Hawking radiation. According to mainstream physics, the maximum amount of information that can fit inside a region of space scales with the area of its boundary, not its volume. That's called the Bekenstein bound, area, not volume. That inversion keeps reappearing. If the universe isn't what we think it is, maybe we've mistaken the projection for the source. Maybe what feels like inside is actually encoded on an outside we cannot directly perceive. You look up at the stars and imagine that their positions are coordinates in an emergent geometry derived from something flatter and more fundamental. It's unsettling, but also strangely economical. Reality compressed onto a boundary. Historians still argue whether holography will ultimately unify gravity and quantum mechanics, or whether it will remain a powerful but limited mathematical analogy. For now, it remains one of the most profound hints that space itself may not be as solid and three-dimensional as it appears. You breathe slowly. If the universe is holographic, then depth is a story told by information. The vastness above you, the billions of light years, might be encoded in patterns far more compact than you can imagine. And the night sky, instead of being a window into infinite volume, could be the shimmering surface of a deeper informational reality. Not less real, just structured differently than you ever assumed. Now you take one more step into uncomfortable territory. If space-time might be emergent, if reality might be holographic, then another idea slips in almost uninvited. What if the universe is, in some sense, computational? You're still under that same star-filled sky. But now imagine that the laws of physics are not just descriptions of reality, they are the operating rules of a vast information processing system. This is often called the simulation hypothesis. And yes, it tends to wander into late-night dorm room debates. But beneath the pop culture gloss, there are serious philosophical and even physical questions hiding inside it. A mainstream grounding first, modern physics increasingly describes reality in terms of information. Quantum states encode probabilities. Black holes encode entropy proportional to surface area. Quantum field theory treats particles as excitations of underlying fields. Information is everywhere in the equations. Now add a technological observation. In just a few decades, humans have gone from crude, pixelated screens to immersive virtual realities. Our simulations of physical systems grow more detailed every year. Philosopher Nick Bostrom famously argued in 2003 that if advanced civilizations can simulate conscious beings, and if many such simulations are run, then statistically it's more likely we are inside a simulation than in a base reality. Historians still argue whether that argument is logically sound or fatally dependent on speculative assumptions about future civilizations. It's philosophy leaning heavily on probability. But here's where physics brushes up against the idea. Some researchers have speculated whether the universe shows signs of discreteness at fundamental scales, like pixels in space and time. The Planck length and Planck time set minimum meaningful units in our current theories. Below those scales, our equations stop functioning sensibly. Is that just a limit of our math? Or could it reflect a deeper granularity? A quirky but intriguing suggestion. Some physicists have explored whether high-energy cosmic ray distributions might show anisotropies consistent with an underlying lattice structure, like a grid. So far, no conclusive evidence of such a grid has been found. The universe appears isotropic and smooth at observable scales. Still, the possibility lingers in the cultural imagination. You imagine reality as a colossal computation? Physical constants as parameters? Quantum randomness as probabilistic algorithms? But here's the critical point. Even if the universe were a simulation, the physics inside it would still be real to its inhabitants. Gravity would curve spacetime. Stars would fuse hydrogen. You would still feel the ground beneath your feet. A simulated black hole still behaves like a black hole within the rules of the system. Historians still argue whether the simulation hypothesis is scientifically testable at all. If the simulation is sophisticated enough, any attempt to detect the code could itself be simulated. That makes falsifiability tricky, a key criterion in science. Some have suggested that limits on computational resources might reveal themselves as constraints in physical law. For instance, the maximum speed of light could be interpreted as a bandwidth limit. Quantum indeterminacy might reflect optimization shortcuts, but these interpretations are metaphorical. There is currently no empirical evidence that we are inside a programmed environment. And yet, the deeper idea that the universe at its core might be informational doesn't require literal programmers. It could simply mean that reality is structured more like mathematics and computation than like solid substance. A mainstream anchor, quantum mechanics, describes systems using wave functions that encode probabilities. Upon measurement, outcomes appear discrete. Information plays a central role in how quantum states evolve and interact. Some interpretations of quantum mechanics, like John Wheeler's it from bit proposal, suggest that physical reality arises from informational yes-no questions at the most fundamental level. It from bit, being from binary. You pause with that. If the universe isn't what we think it is, maybe it isn't fundamentally made of particles or fields, but of information. Not necessarily a video game, but a relational network of bits, probabilities, and correlations that give rise to the illusion of solidity. Historians still argue whether this informational turn in physics represents deep ontological truth or merely a convenient language for describing quantum phenomena. You look up at the stars again. They don't look like code. They look ancient and steady. But then again, so does a high-resolution digital image, until you zoom in far enough. The idea that reality could be computational is unsettling, yes. But it's also oddly consistent with the way modern physics keeps translating matter and energy into equations about information. And even if we are not in a literal simulation, the deeper shift remains. The universe might not be built from stuff in the way classical intuition suggests. It might be built from rules, from structure, from relationships. If so, then asking what is the universe made of becomes less about substance and more about pattern. And the stars above you might not just be burning spheres of plasma. They might be stable configurations in an unimaginably vast informational system, running, evolving, computing itself into existence moment by moment. Now you let the computational idea fade slightly into the background and turn towards something even stranger, something that has already been experimentally confirmed, yet still refuses to fit comfortably inside your intuition. Quantum mechanics. You're standing beneath the night sky again, but this time imagine zooming inward instead of outward. Past skin, past cells, past molecules, down into atoms, into electrons that don't orbit neatly like tiny planets, but exist as probability clouds. A mainstream anchor grounds you. Quantum mechanics is the most experimentally successful theory in the history of science. Its predictions have been confirmed to astonishing precision, sometimes to more than 10 decimal places. Transistors, lasers, MRI machines all depend on it, so this isn't fringe territory. And yet quantum mechanics tells you that particles can exist in superpositions, multiple possible states at once until measured. That entangled particles can remain correlated across vast distances, such that measuring one instantly influences the state description of the other. In 2022, the Nobel Prize in Physics was awarded for experiments confirming violations of Bell's inequalities, demonstrating that quantum entanglement cannot be explained by local hidden variables. That's mainstream, recent, and profound. Reality at small scales does not obey classical intuitions about locality. You pause with that. Locality, the idea that objects are only directly influenced by their immediate surroundings, seems obvious, but quantum experiments show correlations that defy classical explanation. Historians still argue whether quantum mechanics implies that reality is fundamentally non-local, or whether our classical notions of space and causality are simply incomplete descriptions of a deeper structure. Now connect that to the cosmos. If entanglement can link particles across kilometers in a laboratory, what does it mean for the early universe, where everything was once compressed into an unimaginably small region? Some physicists propose that large-scale cosmic structure may retain subtle imprints of primordial quantum correlations. The fluctuations seen in the cosmic microwave background are believed to originate from quantum fluctuations stretched to cosmic size during inflation. That's a mainstream claim. Tiny quantum ripples became galaxies. You imagine that? The Milky Way born from microscopic uncertainty. That alone blurs the boundary between quantum weirdness and cosmic order. But it gets stranger. There's a growing body of theoretical work suggesting that space-time geometry itself may be built from entanglement. In certain models, if you mathematically reduce entanglement between regions, the effective spatial connection between them shrinks. In extreme cases, space-time can tear. It's as if entanglement is the glue holding space together. A quirky but fascinating idea emerges from this. Wormholes, those hypothetical tunnels through space-time, may be mathematically equivalent to pairs of entangled particles. This conjecture, sometimes summarized as ER equals EPR, connects Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen entanglement. It's speculative but grounded in serious theoretical work. If true, then geometry and quantum information are two sides of the same coin. Historians still argue whether these ideas represent poetic mathematical coincidences or glimpses of a deeper unification between gravity and quantum theory. You breathe slowly. If quantum mechanics is not just a microscopic oddity, but a foundational layer from which space-time emerges, then the universe may not be built from solid blocks at all. It may be woven from probabilities, and probabilities don't behave like bricks. They interfere. They superpose. They correlate without classical signals passing between them. Looking up at the stars again, you realize something quietly radical. The vast, structured cosmos may ultimately rest on uncertainty. Not ignorance, uncertainty. A mainstream clarification steadies you. Quantum randomness is not the same as chaos. It follows precise statistical laws. The Schrödinger equation evolves deterministically. Only measurement outcomes appear probabilistic. But what constitutes a measurement? That's still debated. Historians still argue over interpretations of quantum mechanics. Copenhagen, many worlds, pilot wave, objective collapse. Each preserves the mathematical structure, but tells a different story about what reality actually is. If the universe isn't what we think it is, quantum mechanics may be the deepest clue, because it already tells you that reality does not behave like everyday objects. Particles are not tiny billiard balls. They are excitations of fields or wave functions, or branches of a universal quantum state, depending on interpretation. And if entanglement truly underlies space-time itself, then the cosmos is less like a collection of separate objects and more like a single, deeply interconnected whole. Distance becomes secondary. Separation becomes contextual. The night sky above you, so seemingly divided into points of light, might be a tapestry of correlations woven at the quantum level. If that's true, then the universe isn't just stranger than you imagine. It's stranger than classical imagination allows. And the weirdness isn't at the edges. It's at the foundation. Now you let your gaze stretch outward again, not into quantum foam this time, but into geometry, the shape of the whole. Because even if the universe began in a hot, dense state, even if dark matter and dark energy are real, even if space-time emerges from quantum entanglement, there's still a deceptively simple question, lingering in the background. Is the universe finite or infinite? You look up at the night sky and it feels infinite. Stars in every direction, darkness stretching forever, but feeling is not geometry. A mainstream anchor grounds you, measurements of the cosmic microwave background, particularly from the Planck satellite, indicate that the universe is spatially flat to within extremely tight margins of error. Flat in cosmology doesn't mean two-dimensional. It means that on large scales, the geometry of space follows the rules of Euclidean geometry. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees. In general relativity, there are three broad possibilities for cosmic geometry. Positive curvature, like the surface of a sphere, negative curvature, like a saddle, or flat. Current data strongly supports flatness. But here's the catch. Flat does not automatically mean infinite. A flat universe can still be finite if it has a non-trivial topology, like a video game map where traveling far enough in one direction brings you back to where you started. You imagine walking endlessly in a straight line through space, only to eventually return to your starting point without ever turning around. That would mean space wraps around itself in higher dimensions. A quirky but real area of research. Cosmologists search for repeating patterns in the cosmic microwave background that might indicate a finite multiply connected topology. So far, no conclusive evidence of such circles in the sky has been found, but the possibility remains open. Historians still argue whether the observable universe, the part we can see, limited by the speed of light and cosmic expansion, is only a tiny patch of a much larger, possibly infinite whole. And here's the subtle shift. The observable universe is about 93 billion light-years in diameter. That number accounts for expansion during the time light has traveled. But beyond that horizon, there could be more, much more, possibly infinitely more. If space is truly infinite and roughly uniform on large scales, then statistically, there may be regions out there identical to ours. Same distribution of galaxies, same Earth, same you, reading these same thoughts. That's not mysticism. It's a consequence of infinite repetition under certain assumptions of uniformity. You pause. Somewhere beyond your observable horizon, another version of you might be wondering whether the universe is infinite. Historians still argue whether this kind of reasoning is meaningful physics or speculative extrapolation beyond testable limits. After all, by definition, regions beyond the cosmic horizon cannot be observed directly. So how do you distinguish between infinite and merely very large? You can't, at least not yet. A mainstream clarification steadies you. Current observations constrain curvature very tightly. If the universe is curved, the radius of curvature must be far larger than the observable universe. That makes it appear effectively flat to us. But effectively flat isn't the same as truly infinite. You imagine the universe as the surface of a balloon. From the perspective of an ant crawling on it, the surface may seem flat locally. Only by surveying vast distances would curvature become apparent. Perhaps we are cosmic ants, limited by horizon and time. And then there's the philosophical weight of infinity itself. An infinite universe implies infinite matter, infinite events, infinite variations. Every possible configuration allowed by physics would occur somewhere, infinitely many times. That's dizzying. If the universe isn't what we think it is, maybe it's not bounded in any intuitive way. Maybe the observable patch is just a small tile in an endless mosaic. Or perhaps space is finite but unbounded, wrapping in dimensions we cannot visualize. Historians still argue whether infinity is physically real or merely a mathematical abstraction that our theories permit, but reality avoids. Some physicists are deeply uncomfortable with actual infinities in nature. Others accept them as inevitable consequences of inflationary cosmology. You look up again. The stars don't reveal edges. They don't reveal repetition. They just shine. But geometry hides beneath that glow. If the universe is finite, then it has a total size, perhaps unimaginably large, but ultimately bounded. If it is infinite, then everything you see is just a tiny sample of an endless expanse. Either way, your observable horizon is not the boundary of existence, only the boundary of light's travel time. And that realization alone reshapes your sense of scale. You're not standing at the center of a cosmic sphere. You are standing inside a bubble of visibility, surrounded by potentially vast or infinite unknown. If the universe isn't what we think it is, its shape might be far stranger than our three simple categories suggest. Flat, curved, wrapped, infinite. The geometry above you might extend forever, or loop back quietly on itself. And you may never know which. Now that you've stretched space toward infinity, you let your mind fracture it entirely. Because if one universe can exist flat or curved, finite or infinite, why assume there's only one? You stand beneath the night sky again, but this time imagine that beyond your cosmic horizon lies not just more space, but entirely separate regions with different physical properties, different constants, different histories. Welcome to the multiverse. Before your eyes roll too hard, let's anchor this carefully. A mainstream foundation first. Cosmic inflation, the rapid expansion believed to have occurred fractions of a second after the Big Bang, explains several observed features of our universe, including its flatness and the uniformity of the cosmic microwave background. Inflation isn't a fringe idea. It's widely supported by observational data. But many models of inflation naturally lead to something called eternal inflation. In these models, inflation doesn't stop everywhere at once. It ends in localized regions forming bubble universes, while continuing elsewhere. Each bubble becomes its own universe, potentially with different physical constants or properties. That's not fantasy layered on top of physics. It emerges from certain inflationary equations. Historians still argue whether eternal inflation is an inevitable consequence of inflationary theory or just one family of models among many. The mathematics allows it, but does reality follow that branch? You imagine our universe as one bubble in a vast cosmic foam. Each bubble expands, cools, forms its own galaxies and stars. But the underlying inflationary field keeps generating new bubbles indefinitely. Now add another layer. String theory, a candidate framework for unifying gravity in quantum mechanics, predicts an enormous landscape of possible vacuum states. Each vacuum state corresponds to different values of physical constants. If eternal inflation populates that landscape, then different universes could realize different physical laws. Some might have stronger gravity, some weaker electromagnetism, some might never form stable atoms. You pause with that. In such a multiverse, our universe's life-friendly constants wouldn't be uniquely tuned. They would simply be one set among many. This connects directly to the fine-tuning problem. Certain physical constants appear delicately balanced to allow stars, chemistry, and life. Slight variations could render the universe sterile. Historians still argue whether fine-tuning implies deeper physical necessity, mere coincidence, or anthropic selection within a multiverse. The anthropic principle suggests we observe this particular set of constants because only universes with such values can host observers. It's controversial. Some physicists embrace it reluctantly. Others resist it fiercely, arguing that science should seek dynamical explanations rather than statistical inevitability. A quirky but striking example, if the cosmological constant, dark energy density, were even modestly larger, galaxies might never have formed because accelerated expansion would prevent matter from clumping. Yet its observed value is extraordinarily small compared to naive quantum predictions. In a multiverse framework, that small value might simply be one of many possible values, and we happen to inhabit one compatible with structure. You breathe slowly. If the multiverse is real, then our universe is not the whole story. It's a local chapter in a far larger anthology. But here's the challenge. How do you test it? By definition, other universes would lie beyond our observable horizon. Direct observation seems impossible. Some speculative proposals suggest collisions between bubble universes might leave imprints in the cosmic microwave background, circular anomalies, or unusual temperature patterns. So far, no definitive evidence has emerged. Historians still argue whether the multiverse is scientific speculation grounded in theory or metaphysical extrapolation beyond empirical reach. The debate is intense because it touches on the philosophy of science itself. What counts as explanation? If a theory predicts a multiverse as a consequence of otherwise successful equations, do we accept it, even if we cannot observe the other universes directly? You look up at the stars again. The idea that there might be other universes doesn't make this one less real. But it does make it less singular. Somewhere, perhaps, a universe where gravity is slightly stronger, forming smaller, denser stars. Somewhere, a universe expanding too quickly for galaxies. Somewhere, no chemistry at all. And somewhere, perhaps, universes nearly identical to this one, branching from quantum possibilities if you favor the many worlds interpretation of quantum mechanics, which itself suggests that every quantum event spawns divergent realities. Historians still argue whether many worlds is an elegant solution to quantum measurement or an extravagant multiplication of realities. But you see the pattern forming. The more deeply physics probes the foundations, the more singular certainty dissolves into multiplicity. One universe becomes many, one timeline becomes branches. One set of constants becomes a landscape. If the universe isn't what we think it is, maybe it isn't even the universe. Maybe it's one instance among countless variations. You stand quietly beneath the night sky. It feels singular, immediate, personal, but the equations whisper something larger. The cosmos may not be a solitary structure expanding into emptiness. It may be one bubble in an ever-generating sea of possibility. And if that's true, then reality is not just vast, it's plural. Now you narrow your focus again, not to the size of the universe, but to its rules, the constants. The numbers that quietly govern everything from the glow of stars to the chemistry in your bloodstream. Because here's a deceptively simple assumption built into physics. The laws of nature are the same everywhere and everywhen. Gravity has the same strength in distant galaxies as it does here. The speed of light is constant. The fine structure constant governing electromagnetic interactions does not drift with time. That assumption is called the cosmological principle when applied broadly. The universe is homogeneous and isotropic on large scales, and the laws of physics are universal. It's a mainstream foundation of modern cosmology. Without it, interpreting distant light would become nearly impossible. But what if the constants aren't truly constant? You stand beneath the stars and imagine that billions of years ago, gravity was slightly stronger, or that in some distant region of the cosmos, electromagnetism behaves just a little differently. Tiny changes in constants can have dramatic consequences. If the strong nuclear force were slightly weaker, atomic nuclei might not hold together. Slightly stronger, and stellar fusion could proceed very differently. Historians still argue whether the apparent fine-tuning of these constants implies deep physical necessity or reflects selection bias within a multiverse. But another possibility exists. Maybe the constants evolve. A mainstream anchor keeps this grounded. Physicists have tested whether constants vary over cosmic time by examining light from distant quasars. As light passes through interstellar gas clouds, it produces absorption lines that depend sensitively on the fine structure constant. By comparing those lines from billions of years ago to laboratory measurements, scientists can look for drift. So far, results are consistent with constants being constant within very tight limits. But some studies have hinted at tiny spatial variations, though these remain controversial and unconfirmed. The margins are razor thin, but even the possibility cracks the door open. Imagine if the speed of light, about 299,792 kilometers per second, was not fixed in the early universe. Some speculative models propose varying speed of light scenarios to address cosmological puzzles traditionally solved by inflation. These models are not mainstream replacements, but they are seriously explored alternatives. A quirky but fascinating historical note: Paul Dirac once speculated in the 1930s that certain fundamental constants might vary over cosmic time. His large numbers hypothesis attempted to connect seemingly unrelated dimensionless constants. Though his specific proposal didn't pan out, the question lingered. Historians still argue whether dimensionless constants like the fine structure constant, 137, are arbitrary values or emergent from deeper principles. Why 137? Why not 100? You feel the weight of that number? It governs how strongly electrons interact with photons. It shapes atomic structure, chemistry, biology, and we don't know why it has that value. If the universe isn't what we think it is, maybe these constants aren't fixed dials but dynamic quantities set by underlying fields or vacuum states. In some theories, constants depend on the configuration of extra dimensions curled up at microscopic scales. Slight shifts in those dimensions could subtly alter physical behavior. You imagine the cosmos not as governed by rigid laws etched in stone, but by parameters that emerged during symmetry-breaking events in the early universe. When the universe cooled after the Big Bang, fundamental forces separated, gravity distinct from electromagnetism and nuclear forces. Perhaps constants were frozen in during those transitions. If conditions had differed slightly, the freeze-in values might have been different. Historians still argue whether future theories, perhaps a fully realized quantum gravity framework, will derive these constants from first principles, eliminating their apparent arbitrariness, or whether some numbers are simply environmental facts about our cosmic region. You look up again. The stars shine with predictable luminosity curves. Atomic spectra from distant galaxies match laboratory spectra with astonishing precision. That consistency is a triumph of physics. But consistency observed within our horizon doesn't guarantee universality beyond it. That's the subtle edge. If constants vary slightly across space or time, the universe would not be a perfectly uniform arena. It would be patchy in its very laws. Imagine traveling far enough to find a region where chemistry behaves differently, where stars burn at altered rates, where perhaps stable carbon never forms. A strange thought, but not entirely forbidden by speculative models. You breathe slowly. The comfort of physics lies in its reliability. Drop a ball, it falls. Hydrogen fuses in stars the same way everywhere we look. But the deeper question remains open. Are these constants fundamental and immutable, or are they environmental settings in a larger cosmic system? If the universe isn't what we think it is, maybe its laws are not universal commandments, but local bylaws, stable here, perhaps different elsewhere. And the night sky above you, so consistent and dependable, might be one region where the numbers align just right. Now you let go of space. You let go of constants. You let go even of the idea that the universe evolves in the way you intuitively imagine. Because what if time itself is not fundamental? You stand beneath the stars and notice something subtle. Everything you experience is filtered through time. Thoughts unfold sequentially, causes precede effects. The universe has a past, a present, a future. But physics at its deepest level is strangely indifferent to that flow. A mainstream anchor grounds you. Most fundamental equations of physics, Newton's laws, Maxwell's equations, even the Schrödinger equation are time-symmetric. They work equally well if you replace time tt with minus ttt. In other words, the basic laws don't prefer forward over backward. And yet you experience a clear arrow of time. Ice melts. It doesn't spontaneously reassemble. Stars burn fuel. They don't unburn it. That arrow is usually explained by entropy. The second law of thermodynamics states that in an isolated system, entropy, often described as disorder, tends to increase over time. The universe began in a state of remarkably low entropy. Since then, entropy has been rising. That gives time its direction. But here's the mystery. Why did the universe begin in such a low entropy state? Historians still argue whether this initial condition requires a deeper explanation or whether it's simply a brute fact about cosmic beginnings. Some proposals link it to inflation. Others suggest new principles about gravitational entropy. You imagine rewinding the cosmic film, galaxies compress, stars unburn, entropy decreases. The mathematics allows it. But probability overwhelmingly favors the forward direction. So time's arrow may be statistical, not fundamental. Now take one more step. In certain approaches to quantum gravity, like the Wheeler-DeWitt equation, time disappears entirely from the fundamental description. The equation describing the quantum state of the universe contains no explicit time variable, no ticking clock, just a static wave function describing all possible configurations at once. That's unsettling. It suggests that what you perceive as flow might be emergent, like temperature arising from microscopic motion. A quirky but profound analogy. Imagine a flip book. Each page contains a static image. When you flip through them quickly, motion appears. But motion isn't in any single page. It's in the sequence and your perception of it. Some physicists propose that time may be similar, a parameter emerging from correlations between quantum states rather than a fundamental ingredient. Historians still argue whether time is an illusion, as some theoretical physicists boldly claim, or whether that language overreaches beyond what the mathematics justifies. Because here's the tension. Your entire conscious experience depends on temporal ordering. Memory requires past. Anticipation requires future. Causality requires sequence. If time is emergent, then your sense of now might be a feature of how your brain organizes information within a timeless underlying reality. You breathe slowly. Imagine the entire history of the universe, past, present, future, existing as a single four-dimensional structure, sometimes called the block universe. In this view, time is another dimension like space. All events are equally real. You simply move along your world line, experiencing them sequentially. That's a mainstream interpretation of relativity, but it conflicts with your intuitive sense of dynamic becoming. Historians still argue whether the block universe implies determinism or whether quantum indeterminacy preserves genuine openness. Now imagine something even subtler. Perhaps time emerges from entanglement and thermodynamic gradients. Some researchers propose that time's flow arises from increasing entanglement between subsystems. As correlations build, entropy increases, and temporal direction appears. If so, then time might not be a universal river. It might be a local effect tied to information processing. The early universe, being more uniform and lower in entropy, may have had a different texture of time than the current one. That's not mystical. It's a reflection of thermodynamic conditions. You look up at the stars, they seem timeless, eternal, but they too are aging, fusing hydrogen, marching toward entropy's increase. If the universe isn't what we think it is, perhaps the deepest illusion is not space, not matter, not even constants, but time itself. Maybe the cosmos is not a story unfolding. Maybe it is a vast, static structure within which sequences are perceived by conscious systems embedded inside it. Historians still argue whether future physics will restore time to a fundamental role or demote it fully to an emergent phenomenon. For now, the equations whisper ambiguity. Time may not flow. It may be a pattern, and you, standing beneath the stars, may be a configuration within that pattern, experiencing motion through something that, at the deepest level, does not move at all. Now you shift your attention to something deceptively simple, what you can see, because no matter how vast or strange the universe may be, you are confined to a sphere of visibility, a cosmic horizon. You stand beneath the stars and imagine a glowing bubble centered on you, about 46.5 billion light-years in every direction. That's roughly the radius of the observable universe, the maximum distance from which light has had time to reach us since the Big Bang, accounting for expansion. That's a mainstream cosmological measurement. But here's the twist. That boundary is not an edge of the universe, it's an edge of your information. Beyond it, space almost certainly continues. Galaxies exist whose light will never reach Earth because space between us expands too quickly. Dark energy ensures that some regions are permanently causally disconnected. You pause with that. There are galaxies out there right now, fully formed, glowing, dynamic, that you will never observe. Not because they don't exist, but because the structure of space-time prevents their light from ever arriving. Historians still argue whether such permanently unobservable regions should be considered part of our universe in a meaningful scientific sense. After all, science relies on observation. If something can never influence us, does it belong in our physical theory? Yet general relativity and the cosmological model strongly imply their existence. You imagine the observable universe as a flashlight beam in a vast dark ocean. The beam illuminates a region, but the ocean extends beyond the light. Now consider something subtler. As the universe ages and expansion accelerates, the observable horizon changes. Some galaxies currently visible will eventually slip beyond it. Future observers, trillions of years from now, might see only their local gravitationally bound cluster. The cosmic microwave background will redshift into undetectability. Evidence of the Big Bang itself could vanish from view. That's not speculation. It's a prediction of standard cosmology under continued dark energy dominance. Historians still argue whether intelligent civilizations arising in that far future would infer a static, isolated universe because the broader evidence had faded beyond reach. In other words, cosmic knowledge is time-dependent. You are living in a particularly fortunate epoch, able to observe distant galaxies, measure cosmic expansion, detect the microwave background. That might not always be possible. Now take the idea further. If your observable horizon defines what you can know, then any theory about the total universe is necessarily extrapolated beyond direct evidence. We assume homogeneity and isotropy extend beyond what we can see. The cosmological principle works beautifully within our horizon. But beyond it, we don't know. A quirky but fascinating concept arises in inflationary cosmology. Our observable universe could be a tiny patch within a much larger inflating region. Beyond our horizon, conditions could vary, perhaps slightly, perhaps dramatically. You breathe slowly. Every map of the cosmos you've ever seen is bounded by that horizon. It feels comprehensive. But it's not the whole. If the universe isn't what we think it is, perhaps the deepest illusion is that what we observe is representative of the totality. It might not be. The observable universe could be like a single tile in an immense mosaic whose broader pattern you cannot perceive. Historians still argue whether cosmology will ever escape this horizon problem. Can we infer global properties reliably from local observations? Or are we forever limited to a cosmic sample size of one? You imagine being inside a foggy valley. You map the terrain you can see and assume the landscape continues similarly beyond the mist. It's a reasonable assumption, often correct, but not guaranteed. Now look up at the stars again. Their light carries information from billions of years ago. But even that ancient light is bounded by cosmic expansion. There are events happening right now beyond your horizon that will never be part of your past light cone. That phrase, past light cone, reminds you that space-time itself constrains knowledge. If time and space are structured the way relativity suggests, then ignorance is built into the geometry of reality. And that's not a failure of technology. It's a fundamental limit. You feel the quiet weight of that. The universe may be vastly larger than what you can observe, or fundamentally different beyond your horizon, or structured in ways your local patch cannot reveal. If the universe isn't what we think it is, perhaps it's because we mistake our bubble of visibility for the whole ocean. You stand quietly beneath the night sky. The stars shimmer within your cosmic flashlight beam. Beyond that beam lies darkness, not necessarily empty, but unreachable. And no matter how powerful your telescopes become, there will always be a boundary where light has not yet, and may never arrive. The universe you know is the universe that has had time to speak to you. The rest remains silent. Now you let the darkness beyond the horizon fade gently, and instead you turn inward, toward something almost embarrassingly abstract. What if the universe is not made of matter, or energy, or even information, but of mathematics? You stand beneath the stars and consider a quiet fact. Every successful physical theory is written in mathematical language. General relativity is geometry. Quantum mechanics is linear algebra in Hilbert space. Electromagnetism is expressed in differential equations so elegant they fit on a single board. And here's the mainstream observation. Mathematics doesn't merely describe physical behavior, it predicts it. Paul Dirac's equations predicted the existence of antimatter before it was observed. Einstein's equations predicted gravitational waves a century before we detected them. The math knew before we did. That strange effectiveness has puzzled thinkers for decades. Physicist Eugene Wigner famously called it the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract symbols invented in human minds map so precisely onto the structure of reality? Historians still argue whether mathematics is discovered existing independently of us or invented as a descriptive tool that happens to fit. Now imagine taking the boldest step possible. Physicist Max Tegmark proposed something called the mathematical universe hypothesis. In this view, the universe doesn't just follow mathematical laws, it is a mathematical structure. Physical existence and mathematical existence are the same thing. You pause, that's a leap. Instead of matter being primary and math describing it, math is primary and matter is a manifestation of it. In this framework, every consistent mathematical structure exists in some sense. Our universe is one such structure, self-consistent, internally lawful, capable of supporting observers. It sounds like philosophy wrapped in equations, but it emerges from a serious observation. Physics increasingly strips away human concepts and replaces them with abstract structures. Particles become representations of symmetry groups. Forces become gauge fields. Space becomes a manifold. Reality grows more mathematical the deeper you probe. A quirky but grounding detail. When physicists classify elementary particles, they do so using group theory. Pure mathematics developed long before anyone knew it would describe quarks and leptons. Symmetry principles dictate particle interactions. The universe seems to care deeply about symmetry. Symmetry is mathematics. Historians still argue whether this trend reflects a fundamental truth about reality or simply the fact that mathematics is flexible enough to model anything given enough abstraction. You imagine the cosmos as a vast equation, not written in chalk, not computed step by step, but existing timelessly as a complete structure. Galaxies are solutions to field equations. You are a stable configuration in a high-dimensional state space. If that's true, then asking why does the universe exist might be like asking why does the number 2 exist? In a purely mathematical ontology, existence isn't something that happens. It's something that is. That's both comforting and dizzying. Comforting because mathematics feels eternal, stable, unchanging, dizzying because it removes the warmth of narrative. There's no beginning, no becoming, just structure. Historians still argue whether the mathematical universe idea is testable or whether it blurs into metaphysics. Critics point out that not every mathematical structure appears physically realized. Supporters counter that perhaps all are, but we inhabit one compatible with observers. You look up at the stars again, they don't look like equations, they flicker, they burn, they feel immediate. But then again, the orbit of Earth around the Sun can be described by a simple mathematical curve. The spectrum of starlight matches precise atomic transition equations. The expansion of the universe follows a metric solution. It's math all the way down. If the universe isn't what we think it is, maybe it isn't a thing in the conventional sense at all. Maybe it's a solution space, a self-consistent structure in an abstract mathematical landscape. In that case, the question shifts. Not what is the universe made of, but what structure are we? You breathe slowly. The stars above you may not be glowing balls of plasma in some ultimate sense. They may be nodes in a mathematical object, relationships expressed geometrically. And your thoughts right now, patterns of neural firing, are themselves describable in equations. Historians still argue whether reducing reality to mathematics strips it of meaning or reveals its deepest elegance. Perhaps it does both. The universe may not be a story unfolding in time. It may be a grand, self-consistent theorem within which you are both observer and lemma. And if that's true, then the night sky isn't just vast, it's logically inevitable. Now you turn from equations and abstractions to something far more immediate. You, because in all this talk of holograms, multiverses, emergent spacetime, and mathematical structures, there's one persistent mystery sitting quietly at the center of experience: consciousness. You stand beneath the stars and notice that everything you've contemplated, the Big Bang, dark matter, cosmic horizons, exists for you only as experience, as perception, as awareness. Without observers, what does a universe even mean? Careful. We're not drifting into mysticism. We're staying grounded. A mainstream anchor first. Quantum mechanics includes a measurement problem. The wave function evolves smoothly according to the Schrödinger equation, but when a measurement occurs, outcomes appear definite. Exactly what constitutes a measurement remains debated. Some early interpretations loosely implied that consciousness might play a role in collapsing the wave function. That idea became popular in certain circles. However, most modern physicists favor interpretations where measurement is a physical interaction, not dependent on human awareness. Historians still argue whether consciousness has any fundamental role in quantum processes or whether invoking it is unnecessary and misleading. But here's the subtler question. Even if consciousness doesn't collapse wave functions, it remains deeply puzzling. Physics describes particles, fields, geometry, information. Nowhere in the equations do you find the taste of coffee, the redness of a sunset, the feeling of wonder under a night sky. These subjective experiences, qualia, are not obviously reducible to mathematical symbols. You imagine the universe as pure equations, as information networks, as quantum states. Somewhere within that structure, arrangements of matter arise that begin to experience. How? A quirky but intriguing perspective comes from panpsychism, the idea that consciousness, in some minimal form, might be a fundamental aspect of reality rather than an emergent accident. This view has ancient philosophical roots and has recently resurfaced in serious philosophical debates. It doesn't claim rocks think. It suggests that basic experiential properties might exist at fundamental levels, combining in complex systems like brains. It's controversial, highly debated. Historians still argue whether consciousness is entirely emergent from complex neural computation or whether our current physical framework lacks ingredients needed to explain subjective experience. Now connect this back to cosmology. If the universe produces observers capable of reflecting on it, does that fact carry physical significance? The anthropic principle, in its weak form, simply states that we observe a universe compatible with our existence because otherwise we wouldn't be here to observe it. That's logically sound, if somewhat tautological. But some interpretations suggest deeper interplay between observers and physical reality. In certain formulations of quantum cosmology, the universe's wave function includes all possible histories, with observers embedded within. John Wheeler once proposed the idea of a participatory universe, where observation plays a fundamental role in bringing reality into definite form. That language can easily be overstretched, but it highlights a real tension. Physics describes objective structure, yet all knowledge of that structure passes through subjective minds. You stand quietly beneath the stars. The cosmos doesn't seem to care whether you're watching. Galaxies collide whether observed or not. Supernovae explode in distant darkness. And yet without consciousness, there is no meaning, no interpretation, no question of what the universe is. If the universe isn't what we think it is, perhaps part of the misunderstanding lies in assuming a strict separation between observer and observed. A mainstream grounding steadies you. Neuroscience strongly supports the view that consciousness correlates with brain activity. Damage certain regions and experience changes. Alter neural chemistry and perception shifts. Consciousness appears intimately tied to physical processes. But correlation is not full explanation. Historians still argue whether future neuroscience will fully demystify consciousness as emergent computation or whether new physical principles will be required to bridge the explanatory gap. You look up at the stars again. They shine with nuclear fusion, indifferent to thought. And yet, here you are, an arrangement of atoms contemplating atoms across billions of light years. That reflexivity is astonishing. The universe has become aware of itself through you, not in a mystical sense, just physically. Carbon forged in ancient stars now forms neural circuits capable of modeling cosmic expansion. If the universe is mathematical, you are a self-referential substructure. If it's informational, you are a node reflecting on the network. If it's quantum, you are a macroscopic coherence contemplating microscopic uncertainty. Historians still argue whether consciousness is merely a late evolutionary accident or a fundamental aspect woven into the fabric of reality. But either way, any answer to what is the universe inevitably includes the fact that something within it can ask the question. And that may be the strangest feature of all. You stand beneath the night sky, aware. The stars burn, space-time curves, dark energy stretches the cosmos. And within this vast structure, a small pocket of matter experiences wonder. If the universe isn't what we think it is, perhaps it's not just out there. Perhaps part of the mystery is in here. Now you return to something that feels almost modest after holograms and multiverses and consciousness woven into cosmic structure. Fine-tuning, not the flashy version, not the universe was designed for us slogan you sometimes see floating around, but the quieter, more technical puzzle that keeps theoretical physicists awake at night. You stand beneath the stars and think about numbers again. The strength of gravity, the mass of the electron, the cosmological constant, the ratio between fundamental forces. A mainstream fact anchors you. Small changes in certain dimensionless constants would dramatically alter the structure of matter and stars. For example, if the strong nuclear force were slightly weaker, protons and neutrons might not bind into stable nuclei. Slightly stronger, and stellar fusion pathways would change significantly. Likewise, as we mentioned earlier, the cosmological constant appears extraordinarily small compared to naive predictions from quantum field theory. If it were much larger and positive, accelerated expansion might prevent galaxies from forming. These observations are real. They're not fringe apologetics or internet speculation. They're embedded in serious discussions about cosmology and particle physics. Historians still argue whether these apparent fine-tunings demand explanation beyond deeper physical necessity. There are several paths physicists consider. One possibility, the constants are not actually free parameters. In a future unified theory, perhaps a complete theory of quantum gravity, their values may be derived inevitably from mathematical consistency. What seems adjustable now may turn out to be fixed by deeper symmetry or constraint. Another possibility, the multiverse. If many universes exist with different parameters, then it's not surprising that at least one has values compatible with life. We observe this one because we're here. That's anthropic reasoning. It's controversial, but not unserious. Steven Weinberg used anthropic arguments to estimate the cosmological constant's likely range before its acceleration was measured in 1998. His reasoning was surprisingly close to observation. Still, many physicists are uneasy with anthropic explanations. They feel like giving up on deeper derivations. You imagine tuning a cosmic control panel. Gravity slider slightly up, stars burn faster, perhaps too violently. Slightly down, matter clumps less efficiently. Electromagnetic coupling altered, chemistry destabilizes. But here's the subtle caution. Life adapts to conditions. The fine-tuning argument often assumes life like us. It's possible that different constants might permit different forms of complexity we can't easily imagine. Historians still argue whether fine-tuning is overestimated because we project narrow biological assumptions onto cosmic parameter space. A quirky but grounding detail, some parameters can vary more than popular accounts suggest without completely preventing structure. The allowable ranges for complexity are sometimes broader than simplified presentations imply. So the picture is nuanced. But even with nuance, the numbers feel specific. Why does the electron have its mass and not another? Why are there exactly 3 generations of fundamental particles in the Standard Model? Why does the Higgs field have the vacuum expectation value it does? These are not answered questions. You breathe slowly beneath the stars. If the universe isn't what we think it is, maybe fine-tuning is a clue that we're missing a layer of explanation. Maybe constants aren't arbitrary, they're emergent outcomes of deeper geometry. Maybe they vary across a multiverse. Or maybe our concept of possible values is incomplete because we don't yet understand the full space of physical law. Historians still argue whether future physics will eliminate fine-tuning puzzles the way earlier revolutions eliminated epicycles in planetary motion. What once seemed contrived may become inevitable under new principles. But until then, the delicate balance remains striking. You look up at the stars again. Hydrogen fuses into helium at precisely the right rates to produce long-lived stars. Heavy elements form in supernovae. Chemistry emerges, planets cool, life evolves. The cosmos appears structured in a way that permits complexity, not necessarily designed, but permissive. If the universe were slightly different, perhaps you wouldn't be here to wonder about it. And that fact, simple, unavoidable, keeps resurfacing. Fine-tuning doesn't prove the universe is engineered. It doesn't prove the multiverse. It doesn't prove deeper necessity. But it highlights something subtle. The structure of physical law sits within a narrow corridor that allows observers. And you are one. If the universe isn't what we think it is, maybe it's not random chaos constrained by accident. Maybe it's structured by principles we haven't yet uncovered. Principles that make these constants feel inevitable rather than improbable. Until then, you stand beneath a sky shaped by precise numbers, quietly balanced equations, and forces tuned just enough to let stars burn steadily instead of tearing themselves apart instantly. The cosmos feels stable. But beneath that stability lies a set of values we still don't fully understand. And that unresolved precision is one more crack in the facade of certainty. Now you gently pull back from abstractions and look at something more concrete. Actual cracks in the current cosmological model, not philosophical puzzles, not interpretive debates, but measurable tensions in data. Because if the universe isn't what we think it is, the first hints might not come from grand speculation. They might come from numbers that refuse to line up. You stand beneath the stars again and consider one of the most discussed discrepancies in modern cosmology, the Hubble tension. A mainstream fact anchors this clearly. The expansion rate of the universe, the Hubble constant, can be measured in two main ways. One method uses observations of the early universe, particularly the cosmic microwave background, combined with the Lambda-CDM model. That approach gives a value around 67 kilometers per second per megaparsec. The other method measures the local universe directly, using distance ladders built from Cepheid variable stars and type Ia supernovae. That approach consistently yields a higher value, around 73 kilometers per second per megaparsec. Those numbers may look close. They are not. The difference is statistically significant and has persisted despite increasingly precise measurements. Historians still argue whether this discrepancy reflects subtle systematic errors in measurement or hints at new physics beyond the standard cosmological model. You imagine two clocks that should agree but don't. One tells time based on early universe conditions. The other uses nearby cosmic landmarks. Both are carefully calibrated, yet they disagree. That's not a minor footnote. It's a tension at the heart of our understanding of cosmic expansion. Then there's another puzzle. The S8 tension measurements of how clumpy matter is in the universe, derived from weak gravitational lensing surveys, appear slightly lower than predictions based on cosmic microwave background data. Again, not catastrophic, but persistent. And then there are early galaxy observations suggesting that structure may have formed more efficiently than some simulations predicted. While many initial claims have softened with refined data, questions remain about how rapidly massive galaxies and black holes assembled. A quirky but revealing detail, even the distribution of satellite galaxies around the Milky Way has sparked debate. Some observations suggest they lie in surprisingly thin planes, potentially challenging expectations from dark matter simulations, though the interpretation remains contested. None of these issues alone overturn the standard model, but together, they form a pattern of small inconsistencies. Historians still argue whether we are witnessing the early rumblings of a paradigm shift or simply the normal process of refining an already successful theory. Because here's the thing, Lambda-CDM works remarkably well. It explains the cosmic microwave background with exquisite precision. It models large-scale structure effectively. It accounts for dark matter and dark energy phenomenologically. It is not broken, but it may not be complete. You breathe slowly beneath the night sky. Scientific revolutions rarely begin with explosions. They begin with anomalies. Mercury's orbit didn't fit Newtonian predictions perfectly. Blackbody radiation didn't align with classical theory. The photoelectric effect resisted explanation. Each tension was small until it wasn't. Historians still argue whether current cosmological tensions are at that stage. Some researchers propose new early dark energy components to reconcile the Hubble tension. Others suggest subtle neutrino physics modifications. Still others think improved calibration will resolve the discrepancy within existing frameworks. It's an active debate, and that's the important part. Science is not a static monument. It's a living conversation. If the universe isn't what we think it is, it may reveal that fact not through dramatic contradiction, but through persistent mismatch. Numbers slightly off, structures slightly unexpected, predictions slightly incomplete. You look up at the stars again. They don't betray these tensions. They shine calmly as if the equations beneath them are perfectly settled. But inside observatories and research institutions, the data is scrutinized, error bars shrink, models are tweaked, alternatives are tested, and quietly the possibility lingers. Perhaps dark energy evolves. Perhaps dark matter interacts subtly. Perhaps our assumption of uniformity needs refinement. Historians still argue whether cosmology today resembles physics in the late 19th century, confident, precise, yet unknowingly on the brink of transformation, or whether it resembles a mature field ironing out minor discrepancies. You stand quietly with that uncertainty. If the universe isn't what we think it is, the evidence won't arrive as a cosmic billboard announcing revision required. It will arrive as stubborn data that refuses to fit. And the next revolution, if there is one, may already be whispering in the margins of error. Now you let your thoughts drift forward instead of backward. Because if the universe isn't what we think it is, how would we find out? You stand beneath the stars again, but this time you imagine telescopes not yet built, detectors not yet switched on, equations not yet written. The next clues won't come from imagination alone. They'll come from experiment. A mainstream anchor steadies you. New observatories are already reshaping cosmology. The James Webb Space Telescope is probing early galaxy formation. The Euclid mission is mapping dark matter through weak gravitational lensing. The Vera C. Rubin Observatory is surveying billions of galaxies to study dark energy's influence on structure. These are not distant dreams. They are active instruments or imminent facilities. And then there are gravitational wave observatories. LIGO has already detected merging black holes and neutron stars. The upcoming space-based detector, LISA, will observe lower-frequency gravitational waves, potentially from supermassive black hole mergers, and maybe even relic signals from the early universe. If inflation produced primordial gravitational waves, their signature might one day be detected in the polarization of the cosmic microwave background. That would probe physics at energies far beyond any particle accelerator. Historians still argue whether such a detection would confirm inflation decisively or merely constrain its models. Now imagine something more radical. Suppose a dark matter detector finally records an unmistakable particle interaction, repeated, verified, cross-checked. That would anchor dark matter as tangible physics, not just gravitational inference. Or imagine the opposite. Decades pass, no dark matter particle is ever detected. Meanwhile, new gravitational observations consistently deviate from Lambda-CDM predictions. Modified gravity theories gain traction. Either outcome would change the story. A quirky but exciting possibility, precision measurements of the fine structure constant across cosmic time could reveal tiny variations, forcing revisions to our understanding of physical law. Or neutrino experiments could uncover unexpected properties influencing cosmic evolution. Then there's the frontier of quantum gravity. If experiments probing black hole evaporation, quantum information, or high-energy particle collisions reveal deviations from current theory, we might glimpse the deeper structure beneath spacetime. Historians still argue whether quantum gravity will remain mathematically elegant but experimentally inaccessible, or whether clever observational strategies will expose its fingerprints indirectly. You breathe slowly beneath the night sky. The future of cosmology is not about one grand experiment. It's about convergence, multiple independent probes cross-checking one another, dark energy surveys, gravitational waves, particle detectors, cosmic microwave background polarization maps. If all continue to agree with current theory, confidence deepens. If subtle discrepancies multiply, tension builds, and sometimes tension breaks. You imagine waking up to a headline, "New observation contradicts standard cosmology." At first, skepticism, then replication, then cautious acceptance. Science rarely flips overnight. It bends gradually, then shifts. Historians still argue whether paradigm shifts feel dramatic from the inside or simply like the slow accumulation of evidence that makes alternatives irresistible. You look up at the stars and imagine future generations doing the same. Perhaps they will know what dark matter is. Perhaps they will derive constants from deeper principles. Perhaps they will laugh gently at our confusion. Or perhaps they will still be asking new versions of the same question. Is the universe what we think it is? That may be the most enduring pattern. Each era believes it stands near completion. Each era later discovers it was mid-chapter. If the universe isn't what we think it is, the revelation won't come as magic. It will come as better data, better instruments, sharper math, and a willingness to follow evidence wherever it leads, even if it unsettles comfortable models. You stand quietly beneath the sky, aware that you are living in a transitional moment, not because everything is wrong, but because everything is still being refined. The cosmos has not finished revealing itself, and neither have we finished learning how to ask the right questions. Now you let all of it settle, the dark matter, the shifting constants, the emergent spacetime, the multiverse foam, the fragile horizon of observation, and you ask a quieter question. If we're wrong, what actually changes? You stand beneath the stars again, but this time you're not dissecting equations. You're thinking about perspective. When Copernicus proposed that Earth orbits the sun, daily life didn't change. Bread still baked. Seasons still turned. But humanity's self-understanding shifted permanently. When Hubble showed that the Milky Way was just one galaxy among billions, gravity didn't alter. Atoms didn't reorganize. But our cosmic status shrank and expanded simultaneously. A mainstream historical fact anchors this pattern. Scientific revolutions rarely alter the physical world. They alter our model of it. The equations we use change. The metaphors we live by change. Historians still argue whether paradigm shifts are primarily intellectual events or whether they reshape culture more deeply than we realize. Now imagine that tomorrow we discover dark matter is not a particle but a modification of gravity, or that dark energy evolves over time, or that space-time is definitively emergent from quantum entanglement. Your morning coffee would taste the same, but your place in the cosmos would feel different. If space-time is emergent, then the stage you thought you were standing on is not fundamental. If the multiverse is real, then this universe is not singular. If constants vary, then the laws you assumed were universal are local. Each possibility doesn't destroy meaning, it reframes it. You breathe slowly. For most of human history, the sky was a dome. Then it was a mechanical clockwork. Then an expanding fabric. Now possibly an informational network or a mathematical structure. Each shift didn't make the universe less real. It made it less intuitive, and humans adapted. A quirky but grounding reminder: people once resisted the idea that Earth moves because it felt stationary. Common sense can be misleading at cosmic scales. If the universe isn't what we think it is, the first casualty will be intuition, not reality. Historians still argue whether there is a limit to how abstract our understanding can become before it disconnects from everyday meaning. Can humans truly internalize a holographic, emergent, possibly timeless cosmos? Or do we simply learn to manipulate equations without fully digesting them? You look up at the stars again. They shine regardless of your interpretation. The difference lies in narrative. If the universe is a mathematical structure, then you are a self-aware pattern within an equation. If it's computational, you are a process in a vast informational system. If it's one bubble among many, you are a localized expression of broader cosmic fertility. If space-time emerges from entanglement, then separation is less fundamental than connection. None of those diminish you. In some ways, they elevate the improbability of your existence. You are matter that models the whole. That remains astonishing under any cosmology. Historians still argue whether science ultimately demystifies reality or deepens the mystery. So far, every major advance has done both simultaneously. If we're wrong about key aspects of the universe, it means we are mid-discovery, not misguided. It means reality is richer than our current draft. And that's not unsettling. It's invigorating. You stand quietly beneath the sky, aware that the map in your mind may one day be redrawn. But the stars won't resent the revision. The cosmos doesn't require your certainty. It only invites your curiosity. If the universe isn't what we think it is, then the story is not collapsing. It's expanding just like space itself. And you are fortunate enough to be alive in a moment when the questions are still open. Now you let the questions quiet down. Not disappear, just soften. You're still standing beneath the night sky, but the urgency to solve it has eased. The stars are no longer problems to crack or equations to refine. They are simply there, ancient, patient, luminous. You've wandered through dark matter halos and accelerating expansion. You've stepped across multiverse landscapes and into holographic boundaries. You've loosened space-time, questioned time itself, and considered that the entire cosmos might be mathematics wearing the costume of matter. And here you are, breathing, small, awake. A mainstream truth anchors you gently. Whatever the ultimate nature of reality, the current cosmological model, imperfect as it may be, has extraordinary explanatory power. It predicts the cosmic microwave background. It models galaxy formation. It describes gravitational waves. It lands spacecraft on distant worlds. It works, and yet, as you've seen, it also leaves space for doubt, for refinement, for surprise. Historians still argue whether humanity is approaching a final theory of everything or merely climbing an endless staircase of approximations. Each landing feels solid until another rises above it. But perhaps that's not a flaw. Perhaps that's the design of inquiry itself. You look up at the stars one last time. Imagine them not as fixed truths, but as invitations. Every photon reaching your eyes traveled years, centuries, sometimes millennia. They carry stories written long before your species existed. And yet those stories are only readable because the universe permits stable atoms, reliable physical laws, and conscious systems capable of interpretation. If the universe isn't what we think it has still allowed something remarkable. It has allowed you to wonder about it. A quirky but grounding thought drifts in. The atoms in your body were forged in stellar cores billions of years ago. Carbon from red giants. Oxygen from supernovae. You are not just in the universe. You are materially continuous with it. Whatever reality ultimately is, mathematical, holographic, emergent, plural, you are not separate from it. You are one of its configurations. Historians still argue whether ultimate explanations will feel satisfying or forever abstract. But maybe satisfaction isn't the point. Maybe participation is. You don't need the final blueprint tonight. You only need the openness to let it evolve. The night sky doesn't demand belief in any single model. It simply shines, layer upon layer of interpretation, resting gently upon it. The universe may not be what we think it is. It may be stranger, deeper, more interconnected, less intuitive and more elegant than our current metaphors allow. But whatever its true nature, it has produced structure from simplicity, stars from hydrogen, life from chemistry, and awareness from matter. And that awareness, your awareness, has turned back toward the whole. The questions will continue. New data will arrive. The blueprint will be revised. Some ideas will fade, others will crystallize. But the sky will remain, vast, patient, quietly expanding whether or not we understand why. So you stand there a moment longer, letting uncertainty feel less like a threat and more like an open door. You don't need the universe to be exactly what you think it is. You only need it to be real enough to explore, and it is. The stars shimmer gently overhead, not as answers, but as possibilities.